Students, in the previous lecture we have seen the section 1 thermodynamics and our paper code is CHP 4101 fundamentals of physical chemistry. Here we have seen the revision of the thermodynamics in the previous lecture because our first topic is recapitulation. Here we have seen some definitions. In this lecture we will see Zeroth Law of Thermodynamics, first law of thermodynamics and the work and the different types of the work. So see, first topic is Zeroth Law of Thermodynamics. Consider there are three systems A, B and C. A is connected with B and B is connected with C. C is not directly connected with A, but there is a relation of A and C because of B. See, A is in equilibrium with B and B is in equilibrium with C. And here B is equilibrium with A and C. That's why C is in equilibrium with A. So this is the correlation. A is related to B, B is related to C. That's why C is related to A. And therefore A and C are in thermal equilibrium. If they were brought into contact, there would be no net heat transfer. Means heat is constant. So consider a triangle. Here is A, B and C. When A is connected with B, B is connected with C and C is connected with A. This is a cycle. That's why there is no heat transfer and heat is constant. And this is the zeroth law of thermodynamics. Simply, it shows that it's a thermodynamic equilibrium between three systems. Now, the first law of thermodynamics, and this law you know very well. The first law of thermodynamics is related to conservation of energy, and here the energy cannot be created, cannot be destroyed, but it can be converted from one form of energy to the another form. This is our first law of thermodynamics, and it is useful for thermodynamic systems. The law of conservation of energy states that the total energy of an isolated system is constant. Energy can be transferred from one form of energy to the another form, but cannot be created or destroyed. So this is our first law of thermodynamics, and statement is here. First law of thermodynamics, du means change in internal energy is equal to dq plus dw. Q means heat and W is the work. Then work of compression and expansion, free expansion, then expansion against constant pressure and reversible expansion. So these are the four types of work. Work of compression and expansion and free expansion. We will see these topics in today's lecture and remaining two topics in the next lecture. So see, work of compression and expansion. This is our first point. See, this is the first system, suppose, and the pressure is P1 at volume is V1 and there is work which is W. This one is a piston and in this container the gas is filled. So in this system gas is expanded, therefore this mass is increased or height of mass is increased here, and see here the piston applies the pressure on gas and at that time pressure is changed from P1 to P2, volume is changed from V1 to V2 and this piston does work on the system. So see here compression occurs when the surrounding works on the system, and in expansion process system does work on the surrounding. So this is the compression and expansion. So see, here is the diagram which shows expansion and compression again. So work done by gas, this is the expansion process. See here, this is the motion of piston. When piston moves to the upward direction, obviously volume increases, and when volume increases, the system is expanded. And when this arrow, blue arrow, shows there is a pressure which is in the downward direction, and this piston applies pressure on the air or the gas, the height of this air is decreased or volume is going to decrease, volume is changed. This process shows the compression. So this one is the initial process. When the system works on the surrounding, there is expansion, that's why the volume is increased, and when this initial state is compressed by applying the pressure on this piston, the height or the volume of air is decreased or lowered. This one is a compression. So see, when the air is expanded, the molecule loses its kinetic energy and does positive work on the piston. Means here the positive work is there, and here when the air is compressed, the molecule gains kinetic energy and does negative work on the piston. Then this is the diagram again which shows the expansion and compression. So see, here is the first diagram where the pressure is initial pressure Pi, volume is Vi, and this piston, and on the piston there is a mass. When there is an expansion, obviously system does work on the surrounding. Except this, everything is the surrounding, and only this one is the system. So when the gas is expanded, height is increased, and here when the system is compressed, the height of the mass is lowered and the pressure is changed from Pi to Pf and volume is changed to Vf. So this one is our initial state and this one is the final state. This diagram shows the compression, and the system is shown in which compression work is being done on the gas, and the walls of the containers are adiabatic. That means the heat is constant. There is no transfer of heat. Then this is the second diagram for again expansion type of work where electrical work is performed. See here, this is the container which contains the solution in which water is there, H2 and O2 ions are there, and the system is attached to the electrical circuit. And when the mass is lowered and mass is increased, or height of mass is lowered and height of mass is increased, this state is the initial state where the system is at the initial state, and here when the expansion occurred, the mass height is increased, and here the system works on the surrounding. The current produced by a generator is used to electrolyze water and thereby do work on the system, as shown by the lowered mass linked to the generator. And here system also does work on the surroundings through the increase in the volume of the gas phase at the constant external pressure Pi, as shown by the raised mass on the piston. So electrical work is given by equation W electrical is equal to Q into phi. So electrical work is again given by equation I into phi into T. So T is the time, I is the electrical current and phi is the efficiency. Then the work function or the work is not a state function, it is a path dependent. Then consider the following irreversible process, meaning that internal and external pressures are not equal. A quantity of an ideal gas is confined in a cylinder with a weightless movable piston. So, consider this diagram. Here, consider in this container there is a ideal gas which is filled inside the cylinder with a weightless movable piston. Means this piston is weightless and this piston is movable, and the walls of the container or the walls of the system are dithermal, and the system which is shown in this figure, which shows compression work, is being done on a gas. Here compression work is done on a gas and the walls are the adiabatic. That means this cannot transfer heat. Then a gas in a piston and cylinder assembly as shown in figure. So gas is here and obviously this piston is movable, this is weightless, and inside this obviously there is a gas. In this example the system is defined as the gas alone. So only system is the gas. Everything else shown in this figure is in the surroundings. As the gas is compressed, the height of the mass in the surrounding is lowered and the initial and final volume are defined by the mechanical stops. So this mechanical stops, initially system is here. When the compression is done, this piston comes to this stop. So this mechanical stops gives idea about initial volume and the final volume. So from this initial and final volume we can easily calculate the work. So see how work is calculated. So the quantity of work can be calculated by using the definition. Work is equal to integration of F into dx. So this F is the force and dx is the displacement or the change in distance. So see, as we are applying the pressure, obviously we are applying the force on the system, and this piston is moved. That's why there is a change in distance, there is a displacement. That's why work is the force and displacement dependent. That's why work is defined as change in the force and displacement. So equation is here, W is equal to integration of F into dx and limits are xi to xf because the distance is changed from initial to final state. And here is the equation, W is equal to integration limits are xi to xf. F is the force and dx is the change in distance. Now the F into dx, the force is given by equation minus P external into A and dx as it is taken here. So Pex means what? The external pressure we have applied on the system, and the A is the area and dx is the change in distance. Then force is equal to Px into A. So just put this in this equation, and equation is as this. The work will be either positive or negative. So W is equal to minus integration of xi to xf Pex into dV is equal to, now the PEX is the constant pressure we are applying. That's why I take this pressure at the outside of integration. And now change limits because we have replaced this term PEX into dx, and here Px is as it is, and A into dx or area into change in distance is equal to change in volume dV. So next equation is W is equal to minus Px, integration goes from Vi to Vf into dV. So dV is the change in volume. That's why when limits are put here, the equation becomes Vf minus Vi. So just this is the work equation when the compression type of work is done. So W is equal to minus Px in bracket Vf minus Vi. So we will see one problem based on this equation. So problem is here. Calculate the work involved in expanding 20 liter of an ideal gas to a final volume of 85 liter against a constant pressure of 2.50 bar. So see what the data is given in the problem. So see here the final volume is given 85 liter and initial volume is given 20 liter. So we have Vi is equal to 20 liter and Vf is equal to 85 liters. So just convert it into meter cube. 85 into 10 raised to minus 3 meter cube, and this 20 liter is equal to 20 into 10 raised to minus 3 meter cube. So and pressure is given in bar, so convert it into Pascal. 1 bar is equal to 10 raised to 5 Pascal. That's why 2.50 bar is equal to 2.50 into 10 raised to 5 bar. So this is the given data. Now we are going to find out the work. So work is equal to minus P external integration of Vi to Vf into dV. So just write down the final equation. W is equal to minus Pex or external pressure in the bracket Vf minus Vi. Just put values here. Minus 2.50 into 10 raised to plus 5 bar. Bar is converted into Pascal. So 2.50 bar is equal to 2.50 into 10 raised to plus 5 Pascal. In a bracket 85 minus 20 into 10 raised to minus 3 meter cube. So the work is calculated minus 16.3 kilojoules. So this is our problem which is based on this equation. Now the next topic is free expansion, or the next type of work is the free expansion work. So free expansion occurs only when the external pressure is equal to 0 and there is no any opposing force. That's why the overall free expansion in which the work done is equal to 0.